So far, we have defined a random vector like x equal to x1, x2, and xn, and we said that this random vector is characterized either by its probability density function, cumulative distribution function, and so on. So the joint distribution characterizes this random variable. Now we want to define a couple of statistics of these one, which are correlation and covariance matrices. Correlation and covariance matrices for x. First, the mean of x, we have to define it is equal to mean of x1, mean of x2, mean of xn. So this is the mean vector. Sometimes we denote it by mu x. So it's a vector of the same size as random vector. So this is called the first order statistic of a random vector, but the second one is a covariance matrix or correlation matrix of two random vector. So it's quite often used in many applications. So correlation and covariance matrices are important. So if you have for two random variables, the covariance of two random variables we have already defined. So if you consider, like if you have x1, x2, xn, so if you consider one of them, let's say xi from here and put it here, and then like you consider another of them, xj or xk, sorry, put it here, and then you calculate deviation of the first one from the mean, and this is the deviation of the second one from the mean. So we put a conjugate here because if this is complex conjugate, and when you multiply these together, these will have properties of inner product. Specifically, if we consider the variance, which is the covariance of a random variable with itself. So if you put these k equal to I, so it will be the covariance of a random variable with itself. These part will be complex conjugate of these ones. So if you multiply complex conjugate of something by itself, it becomes real. So these will become real random variable, and then when you calculate its expected value, you get this one. So basically, this is equal to inner product of xi minus mu xi, so the deviation of ith random variable from the center, the dot product with xk from its is center. So remember that on the dot product we put a conjugate on this one. So it is very important to put the conjugate on the second one. So we say that a sequence of random variables are uncorrelated if their covariance is 0 for all I and k not equal to each other. For example, if you say a set of complex valued real random variables are uncorrelated, then the sum given by that, this is a linear combination of that. If you calculate variance of these linear combination, will become sum of the variances of each term because they are uncorrelated. So their cross correlation is 0. So only the self correlations or the variances are not 0. So you get these quantities. So this is the most important property of uncorrelated random variables, either complex or real. So if you have a bunch of random variables, real or complex, we want to define sample mean and sample variance. So the sample mean is just you add them up and divide by the number. So you have n random variables. This is called sample mean. That means that you get your data, and then from your data you add them together. Sample variance means that you calculate each of them minus the sample mean, so the deviation from the sample mean. And then you calculate is a squared value and divided by n minus 1. So this is called sample variance. Remember that here we put n minus 1, not n. Okay, so these are standard definitions of sample mean and sample variance in a statistic. So why they put n minus 1, not n, is a reason that we will see perhaps at the end of this course. For instance, if you assume that a bunch of random variables are uncorrelated, suppose that they all have the same mean and they all have the same variance, then you could prove that mean of the sample mean is equal to this. This is easy because mean of this guy is equal to sum of the means, all of them are equal to mu, and then n times mu divided by n, it become equal to this. So and the mean of this guy, it is a bit tricky. If you do that, you will get this one. But if you put, instead of n minus 1, if you would have put n, you would have not got these results. So the result would have been a lot different. So the mean of the sample mean, so the variance of the sample mean, the variance of this guy is 1 over n times variance of this, and the mean of the sample mean is equal to this one. So remember that mean of this one. So if you put here, instead of n minus 1, if you would have put n, let's say if you define, let's say z equal to summation of xi minus x bar to the power of 2 divided by n, summation I equal 1 to n, then mean of z would have been equal to n times divided by n minus 1 divided by n times sigma 2, which is not unbiased. But this guy gives an unbiased estimate of the variance. So what I conclude from here is that V bar is an unbiased estimate of sigma 2, and this is also an unbiased estimate of mu.